Okay. Good afternoon and welcome to Carlin Cymru revision sessions. This session will focus on 2.2 Newton's laws, and that will be at GCSE level. The teacher presenting today will be Mrs. Owen from Penglais School in Aberystwyth. The session will last around 45 minutes, where the teacher will go through the relevant subject content. If you have any questions, please use the question and answer section, and we will endeavour to answer your question during the session. The session will be recorded, with the recording and any relevant resources uploaded to the e-sgol website in the Carlin Cymru area. So without further ado, I'll pass you over to Mrs. Owen.
Thank you very much, Mr. Rid, and I'm sure he will help to answer the questions that you put into chat. Okay, so I have taken here Newton's first law, Newton's second law, and Newton's third law, and I've literally just lifted them from the WJC blending website. So please make use of these. So go on to the WJC digital resources and look for the blended learning, and I've lifted it literally from 2.2 unit 2.2 Newton's laws, and it's very dry, these definitions, and you can either learn these definitions as you see them, and WJC then can't take any marks away from you, or you can learn them. So, for example, Newton's first law of motion states that an object will remain at rest or in uniform motion in a straight line unless acted on by an external resultant force. Now, I think that's a bit of a mouthful. So what I tend to kind of like say to my pupils is, remember that the motion of a body, of anything, can only be changed by an unbalanced force. Now, to get your marks though, you have to quantify what you mean by motion and how it can be changed. So this bit here, the motion can only be changed. What we mean is, does it stay at rest, or does it continue going in a constant speed in a straight line, or does it change? Can it accelerate, or can it decelerate? Okay, and what we mean by a unbalanced force is what we call a resultant force, or a net force, or a external force, or of the system. Okay, so Newton's, so we'll show you a few examples where we can apply the Newton's first law and the Newton's second law. Newton's second law is quite simply F equals ma, but we must remember that that force, I'd say to my guys, remember it's RF equals ma, because it's the resultant force that produces a change in the motion. So Newton's first law is really, in words, what the second law is in an equation. So you've got to have a resultant force, you've got to have an unbalanced force. That's your resultant force that produces a change in motion to give you an acceleration. So you can see quite nicely we've got an equation there, and that is a much easier way of remembering Newton's second law than it is to have to remember Newton's first law. So if you can remember F equals ma, that's your Newton's second law, and then you can kind of like put that equation into a word form for your first law. Now, if you were doing higher, I have had a look at this and they really do want more. If you rearrange this equation, and at higher, they do expect you to be able to rearrange the equations. So we have acceleration here times by the mass. So if we want to get rid of the mass, the resultant force divided by the mass gives you that acceleration. Now, looking at it this way, we say that the acceleration is proportional. That sign means proportional, so that if you double the 1 on the one side, acceleration, then the resultant force doubles, or the other way around. If you double the resultant force, then the acceleration doubles, and we call this proportional, and this is the sign. Whereas the acceleration is inversely proportional to the mass. We can say proportional to 1 over mass, but we tend to say that it's inversely proportional because you'll see that the mass is on the bottom of the fraction. Okay, now if you are doing higher, then that is what is expected for you to have to remember for Newton's second law, not just the equation resultant force equals mass times acceleration. And then what we'll have a look at is how to apply Newton's third law. Now, very often pupils with Newton's third law remember action equals reaction. Now, this will only give you 1 mark. You have to kind of remember that there are 2 objects here that are at play, and if body A exerts a force on body B, then body B exerts an equal and opposite force on A. So clearly we're identifying the two objects, and we're interchanging them from the action to the reaction. So I'll explain what I mean by that by using an example, and I hope that you will be able to see. So what I'm going to do is, for a couple of minutes, I want to show you this Japanese a snowboarder, and just watch this for the a couple for his jump. Can't get it to work. Is it showing anything?
It isn't clear, unfortunately.
No. Okay, I can't. It didn't show anything, did it, Mr. Ridd?
No, unfortunately, the video didn't play.
Okay, all right, okay. So I've got a few shots of him, okay, as he goes along. He won the gold Commonwealth half pipe recently in Beijing, and this is him starting. All right, and have a look on YouTube when you get the opportunity, because it's really quite phenomenal what he manages to achieve. Now, looking at him at the start of the race, he's just standing there. He's just looking at the course ahead of him. All right, so that the force is acting on him, if we kind of like put his center of gravity and the first force acting on him is the weight acting down. Now, he's not falling through the snow at all. The snow is strong enough to support him, and the force kind of like is preventing him from going through the snow is called the contact force. We also call it a reaction, okay, or a reaction force, okay, either or. Now, we say that because he's just standing still, we say that he is the forces on him are balanced, so that there's no change in motion, so there's no resultant force acting on him. Yes, there are 2 forces, but they're equal and opposite to one another, so that the weight is equal to the contact force or the reaction force. And in that situation, he stays still. We say that the resultant force is equal to 0. And because resultant force is proportional to the acceleration, he stays still. Okay, so that is kind of one look at he's not moving, I know, but he's staying stationary because the resultant force acting on him is 0. Now he's started moving down the slope, getting ready to do his jump. Okay, so there is what we call a component of the weight. We have to call it component of the weight because he's going down the slope. It's not his full weight that's acting down the slope, because we know that the weight acts vertically down towards the center of the earth. But we say there's a component of his weight going down the slope. Now, equally, there is a little bit of friction. All right. And when those two forces are the same, so that the friction is equal to the component of the weight, then what we have is a situation where he is going down at a constant speed. So in a sense, when he gets to that constant speed, his motion is not going to change anymore, because there isn't any one force bigger than the other in this situation. The forces are what we call balanced. He's in dynamic equilibrium, and we say that the resultant force again is 0. So therefore, because the resultant force is proportional to the acceleration, and if there's no resultant force, he's not going to accelerate, but he's moving forwards. All right, so that means that he's moving at a constant speed. Okay, now I'm going to say, let's see what happens if we ignore friction now. He's speeding up a little bit more, so I'm going to move on. All right, he's going a little bit faster down the hill. So the component of the weight, I'll put component of the weight, all right, like this. Okay, and he's got, let's say that the friction is now negligible, because there's very little friction compared to the fact that he's going to be moving a lot faster. Maybe there's air resistance, and that air resistance will increase as his speed increases. So when he's first starting out and when he's first moving, that air resistance is not very much, because he doesn't have to get through much air in a certain time period. Say in 1 second, he only has to get through a little bit of air. But as he's speeding up, because this force is very big compared to any other resistive forces slowing him down, then that means that the resultant force is in this direction, i.e. down the slope, and the resultant force tells you that there will be an acceleration, because the resultant force is proportional to the acceleration. So if you've only got the weight, component of the weight going down the slope, this will cause him to speed up going down the slope, because there is a resultant force. So there is an unbalanced force, so he's going to accelerate. Now, as he accelerates and gets faster, that air resistance will get more and more. So the air resistance will become bigger as he gets faster, until eventually it's going to be equal to the weight. So when the weight is equal to the air resistance, we're in that similar situation as before. He's moving down, but he's moving down such that the resultant force is 0 on him. The weight take away the air resistance is how you find the resultant force. You take the two forces away from one another because they're opposing one another. So there will be no acceleration. So therefore, he is going at what we call terminal velocity. And that terminal velocity is the maximum speed that he could be going at. He can't go any faster, all right, because he has got no more weight acting in that direction, all right, unless the slope changes so that the component of the weight is bigger. Now he really does ride into the sky. The half pipe Olympic is such that he kind of he goes from one end and he literally picks up the speed and he's going to fly off at the other end. And this is what he looks like mid-flight. So he is moving upwards. So if I put an arrow going upwards to show you in which direction he's going in, then there are two forces still acting. There's no contact force because he's not in contact with anything. The only contact force is when he's actually got his snowboard on the ground. So here he's got a weight acting down. He's got air resistance. Now, if he's going upwards, then the air resistance will always act to be in the opposite direction to his motion, because he's moving up, he's having to actually try and get through the air going up. So the air resistance also acts down. So what we've got here is a situation where the resultant force is equal to not take them away from one another, but we have to add them up. So the air resistance plus the weight to give you the total resultant force. And in this situation, because he's moving up and the resultant force is downwards compared to him going upwards, then that means that his motion will change, and your force equals mass times acceleration. You've got the force acting downwards, but because he's moving upwards, this acceleration means that it will be decelerating upwards. So what he will do is slow down until he comes to the top of his jump. All right, and then what happens is he starts to move downwards. But how will he move downwards? So again, we've got him now in a tight ball. There are two forces acting again. There's the weight acting down, but because now he's moving downwards, all right, his resultant force in this case, he's got air resistance acting up, he's got the weight acting down, and it all depends on the size of this air resistance to see how much the resultant force is acting in order to know how much he's going to be speeding up. Now, the way that he's got his body here is the air resistance is going to be quite low compared to when he had his body open like this, all right? Which means that the air resistance is going to be a lot lower, so that the resultant force now is equal to the weight take away the air resistance. Remember, he's moving downwards, he's having to get through the air going in the downward direction, so he's having to do work against air resistance, and that air resistance is acting in the opposite direction to his motion. So now the resultant force is the weight take away the air resistance, and the resultant force is equal to mass times acceleration. So the resultant force is acting downwards because the weight will always be bigger than the air resistance in this case. And then what we have is, because it's going downwards, it will accelerate, and it will accelerate in a down direction. Okay, all right. So I just wanted to let's have a look. Okay, so that kind of like shows you, if we go back to the start and I just recap the first and the second laws. So Newton's first law states that an object will remain at rest, i.e. stationary, or in uniform motion, i.e. constant speed or terminal velocity, in a straight line. We can shorten that to it will remain at rest, i.e. stationary, or with a constant velocity, unless it's got a resultant force. All right. Now, Newton's third law, let me show you Newton's third law, or shall I? Yes, I will show you Newton's third law. Then I will go to some skating, because we'll have a look at the forces there. And you can see this distance here that he manages to achieve is over 5.5 meters. Now, I don't know how high the classrooms are where you go, but ours here are 2.5 meters, and that's a standard classroom. So that is over twice the height of your classroom. It's pretty remarkable what he manages to achieve. And notice that his body is very, very compact, and watch that compared to other snowboarders, because he's got his body so compact, his air resistance is actually quite small compared to other people's air resistance. And so he's always kind of like got quite a rapid change of motion, whether he's going upwards or whether he's going downwards. Now, let's have a look at the Newton's third law. This is where you think that the Newton's third law, oh, that's easy. That's just the weight acting down, and surely that's the contact force acting up. Well, it's not as easy as that. I think you have to split it up. Okay, because you've got to say to yourself, for example, this weight here, we know the weight acts down. So the weight is the force, the gravitational force of the Earth on the body, okay, his body. All right. Now, the corresponding reaction to this action of the force due to gravity would be the force of the body on the Earth, but it would be acting in the opposite direction. Now, what do I mean by this? It's not a simple case that the weight and the contact force are the action and the reaction and Newton's third law. That is not the case, all right? So what you've got to do is you've got to identify your two bodies. This is the body here, all right, his body, and this is the Earth here. So those are the two bodies with which the force is acting from and to. So the weight is from the body, the center of mass of the body, or the center of weight, center of gravity, down towards the Earth. All right. So it's the force from the Earth onto the body. All right. So the other reaction force is from the body onto the Earth, and it goes in the opposite direction. And it just doesn't look quite right, does it? It just doesn't feel right, because we're just not used to talking about this, because we're only ever concerned about ourselves. We're not actually concerned about the force that our body does from the Earth. So in fact, here we are, the force of the body on the Earth is equal and opposite to the force of the Earth back on the body. And that is your action and your reaction. But as I say before, no good saying just action equals reaction if you want a full 2 marks. It's okay if you want 1 mark, all right? But if you want the full 2 marks, you've got to identify the two objects. So now you're probably going to ask yourselves, well, what about that contact force? Well, the contact force, if I draw it over here, because it's going to just get a little bit too messy. Here we are, he's here on his snowboard. Okay, getting ready. All right, and the contact force is from wherever he is touching the snowboard here, or here, upwards. Okay, so that is the force of the snowboard onto his feet or the body, let's just say. Okay, and the equal and opposite reaction to that would be the force of his feet, of his body, back onto the snowboard, and it will be in the opposite direction. Perhaps it's easier to see this one by looking at a mug. So if we take a mug, all right, like this on a table, and we've got the force of the mug on the table, that is equal and opposite to the force of the table on the mug. All right, so it's in the opposite directions, so we can say that they are opposite and equal. And that is your action and reaction. You're identifying the two objects in which it is acting over. All right. Now, before we move on to a few exam questions, I want to show you this little clip here. And right, let's have a look, see if this one, right, let's go back. All right, and I will come out of here and I will show you a few of my some sample questions. Now, this is a nice question here, and it just shows you that you have to be able to apply yourself to different situations. And this one here is somebody learning a Segway. You might have seen this question before, and they've tied it in with unit 2.1 with distance and speed time graphs. And they said that he's leaning backwards here between A and B, he's upright here between B and C, and he's he's leaning backwards to slow down. So this would be this DC section. He's upright, I'm assuming he's going at constant speed, so this will be this section, and he's accelerating by going forwards, which would be this section here. So in a situation like this, where you've got an exam question, all right, these are some of the common kind of like misconceptions that pupils do. So I know it doesn't apply to forces, but we'll go through with them. So here they've been asked to use the equation to work out the acceleration. So change in velocity is divided by time. Now, during the first 3 seconds, so they've been given the first 3 seconds, and this candidate's put in the wrong answer there, but they did get the fact that it goes from 0 to 6 meters per second, but they didn't quite see that it was for the first 3 seconds. And notice a very common mistake here is to realize that acceleration units are meters per second, when in actual fact they're meters per second squared. But they did go on to, you know, have the mass and have the acceleration, all right, from the previous section to get the resultant force. Now, this is foundation level, but and it's a good attempt at their questions. Now, this candidate here, all right, has got the acceleration, change in velocity and change in time. So they've read it off correctly and just failed to then put it into the calculator or ask themselves, does that look right? 6 divided by 3. And again, they've made the similar mistake with the unit, but they can, you know, substitute the mass and the acceleration, and they've error carried forward to get their marks. Okay. All right, what else have other people done? Okay, same error on that one. Now, here we are, we have got calculate the resultant force during the first 3 seconds. So they didn't take the acceleration that they worked out from here forward into the question. All right, so always use what you have been doing before to help you with the next part of the question. And this candidate has done the same thing. And then lastly, it says here at the top, between which points A to B or B to C or C to D is the person leaning forward in the segue. So he's leaning forwards to accelerate. Now this person has chosen 2 things. So in effect, he has conned himself, because you can only have, you know, one of those. He can't have 2 sets at all. Okay, so that's kind of foundation. Here is another foundation question. It's a nice little one. Somebody falls out of the tower, okay, and she lands safely on a large airbag underneath. All right, and you've been asked to determine the weight, the mass. You've got the weight here, so the information's been given to you on a diagram. So look around and look. Don't just look in that part of the question. Look in the whole part of the question and the diagram. 1 kilogram weighs 10 newtons, so you've got to divide it by 10 to get your mass, and this person has successfully done that. And then the woman hits the airbag with 5.6 kilojoules of kinetic energy. The airbag stops her in a distance of 2.8. So again, that is 5.6 kilojoules converted into joules, and all you have to do is times it by 1,000. So you're not being asked to calculate with the equations from the front or anything, and they haven't given you an equation to work with. So just go from what information that you've got there, and you know that a kilojoule or a K means 1,000, a kilo means 1,000. Okay, and then lastly here for the foundation question, use the equation mean force equals work done over distance. So the work done, now this candidate failed to realize that the work done is the same thing as the kinetic energy here. So work done is also known as energy transferred. So you look out for an energy. Now I'll go over that in a couple of weeks' time when I do energy transfers, all right? And so they've got the right working, they've got the right equation, but they haven't used their converted units. And that's fine to give you a mark for the working, but it wouldn't give you the final answer. It's suggested that it would be safer if the airbag were filled with water. The distance to stop the same woman falling from the same tower would be 0.8 instead of 2.8. Without further calculation, do you agree with the suggestion? Well, you're going to come to a stop in a much longer time, and therefore if it's a longer time, we can show that force equals mass times acceleration, and you know from unit 2.1 that force equals mass times change in velocity over time. So if somehow you can extend that time it takes to come to a stop, then because it's underneath, all right, that means that the acceleration will decrease. And because the force is proportional to the acceleration, if the acceleration decreases, the resultant force or the force acting on you decreases. And so, okay. All right, so in this case, although, okay, all right. Now I'm going to switch now to a higher question, and I want to kind of like look at kind of like your practical side of physics, as well as kind of like helping you to kind of like deal with the forces. So here we've got a group of students. They're investigating how the terminal speed of a falling paper cake cases depends on their mass. You no doubt have seen this, and you no doubt have had a go at doing this yourself. Now the cake cases were dropped from at least 20 centimeters above the pointer. So that allows them to reach a terminal speed by the time they reach the pointer. So the assumption is that during this fall of 1.5 meters, they are going at a constant speed. And if they are going at constant speed, we can quite simply use the equation speed equals distance divided by time. The time taken for the cake cases to fall, the distance of 1.5, so it's always going to be 1.5 at the top there, divided by the whatever time it takes. All right, and we're going to have to do this several times because there's going to be a reaction error, because the time is going to probably be quite short. So it's probably a good idea to repeat your readings so that we can identify any anomalies and we can discard them from having to try and work out the mean time. So the same cake cases are used throughout the experiment, and state the other controlled variables in the experiment. Well, you want to either drop it from the same height, or you want to drop it through the same distance. Okay, so you want to drop height is going to be the same. Now, you have to be specific what you mean by that. Do you mean from the pointer to the ground, or from where you drop the cake cases and to where you start timing? All right, but so you can't just say height, you have to kind of like be a little bit more specific. So in this case, let's have drop height the same, i.e. from the pointer to the ground. All right, just be specific, and whatever you do, just be specific. Don't write any words like it. Always explain what that it is. Explain the advantage of 5 trial timings for each number of cases. Well, in case there's an oddity, an odd one, and we call that an anomaly. Okay, that means it's an odd result. Now, it's not just the fact that we have one, it's the fact that we identify an anomaly and the fact that we can discount it. All right, and that means that we can make more accurate the mean time. Okay, so more accurate mean time. Don't just say it's more accurate results. Say exactly what is going to be more accurate, because otherwise they won't give you the mark. The students are told the mean mass of the paper cake case. Well, explain how the quality of results collected is affected if the cake cases used each time are weighed rather than calculated by using the mean mass of the cake case. Or maybe each cake case is different, and maybe is different in terms of their mass, and maybe that difference, the difference is significant. If you decide that the difference is not significant, you can also write that so that it's not going to have any effect. But I'm going to say the difference is significant, and therefore you're going to have a more accurate value for the mass of the cake case. All right, but you can go either way, but as long as you explain yourself. Explain in terms of forces how the cake case reaches terminal speed. Well, we've got to do it in terms of forces. No good talking about other things. You've got to talk in terms of forces. So the weight acting down, you've got the air resistance acting up, and when the air resistance, well, it's 0 when it first starts, so the air resistance increases until it's equal to the weight. That means that the resultant force is 0. That means that the forces acting on it are balanced. Okay, now it doesn't need any more than that. It doesn't want to know about the motion, doesn't want to know about acceleration. It wants to know in terms of the forces. All right, so talk in terms of the forces, and then describe how the experiment could be extended to check that the cake cases are falling with a terminal speed over the 1.5. Well, here's my pointer here, and if I let go at 20 centimeters above, then we can time it, you know, of our 1.5 meters, and then perhaps we could do a little bit higher than 20 centimeters, another 20 centimeters higher, and another 20 centimeters higher. And each time, if we find that the time here is the same for each different drop height above the pointer, all right, then we can see that it's going at a constant speed, all right, at each height dropped above. So we just extend this from 20 upwards and see if the time taken across the 1.5 is the same. Okay, and lastly, now this is really quite nasty, okay, this last little bit, but just go across it and just deal with it as you see it. The cake cases use the supplies in a box containing 250 cake cases. The combined mass of the box and the cases is 118 grams, and the mass of the empty box is 18 grams. So automatically I'm going to put 118 grams, take away 18 grams, and that's my 100 grams for 250 cake cases. So that tells me if I've got 250 cake cases, I can measure the weight mass of one of them by doing 100 grams and dividing by 250 cake cases to give me 0.4 grams for each cake case. Now that might come in handy a little bit later on. I'm just dealing with the information as I get it. The terminal speed of the 4 cake cases is 2.54 meters per second. Now the weight, all right, is 1 kilogram is 10 newtons. So the time taken, so let's use speed equals distance divided by time. That means that rearrange it. Now, if you're doing higher, you're expected to be able to rearrange these equations. So time equals distance divided by speed, 1.5 divided by 2.54, and that comes out as 1.5 divided by 2.54 equals 0.59. Pop the answer on the line, otherwise again they won't give you your mark if you don't put it on the line. And then you know that you've got your cake cases here and what forces are acting on them, the weight and the air resistance, and you know that the air resistance is going to be equal to the weight when it's going at terminal velocity, because the resultant force acting on it is 0, because you take the two forces away from one another because they're acting in opposite direction. So if the weight is, well, we don't know the weight, but we do know the mass of each. So if the mass of each is 0.4 grams, and we've got 4 cake cases, so times that by 4, 1.6 grams. And then what we've got to do now is we know 1 kilogram weighs 10 newtons. We've got to divide this by 1,000 to get it into kilograms. So that's 1.6 times 10 to the minus 3 kilograms. And then we've got to times it by 10 to get it into newtons. So that would be 1.6 times 10 to the minus 2. Now you can write it as 0.016, or you can leave it in standard form, 1.6 times 10 to the minus 2. Now I've got a couple of minutes and not a lot of time to answer any questions. So Mr. Ridd, are there any questions to be answered?
No, we can only assume that it was explained very well. So we'll have any questions in the chat. If anyone does have any questions, now would be the time to throw them in. So if you want any questions, if anything is not clear on Newton's first 3 laws, please pop something in the chat now.
Okay.
We're happy to answer.
I'll just recap then. So what we've been doing is looking at the 3 laws of motion. So Newton's first law, you can learn it how they've got it. Or you can, Newton's first law states that an object will remain at rest or in uniform motion in a straight line. You've got to say that straight line, or you just say uniform velocity. unless acted upon by a resultant force. All right. Newton's second law, F equals ma, but if you're doing higher, I'm afraid you're going to have to remember that acceleration is proportional to the resultant force and it's inversely proportional to the mass. And then finally, to finish on, Newton's third law, action equals reaction, will only give you 1 mark, but if you remember, if body A exerts a force on body B, then body B exerts an equal and opposite force on body A, that will give you both marks. Okay, thank you for listening, and in Mr. Ridd will give the session next week, and thank you very much.
Yes, all right, thank you very much, everyone. Next week's session, just so you're aware, will be on radioactive decay and half-life, so make sure you pop along to that one. It's going to be exciting. Yeah. Bye, everyone. See you soon.